Mm-hmm.
Start recording, especially since we're starting off talking about solids, liquids, and gases. This is like September or October of first year chem. Like, what does a solid, liquid, and a gas look like? So it's just before gas law. It's just like, what the hell is a solid? What the hell is a gas? What the hell is a liquid? And they go into way too many details there. So solids. They can come in two different kinds. Not that they ever ask you the difference between these, but crystalline and amorphous. And I don't think that that's really that hard to figure out the difference between. Play-Doh is amorphous. Salt is a crystalline. Like, there we go. If it has some sort of like regular structure, it's a crystal. If it doesn't, it's amorphous. Yeah, but we know that our little particles are close together. We say that they don't really move. The normal term is that they vibrate. Remember, solids vibrate because they're locked in place, so they're vibrating in place.
Miss Baskin?
Yeah.
So apparently Miss Jackson made a Zoom thingy meeting at 10:30. Is anybody going to that? They?
Personally, hers is a check-in. We're not really learning, so I may stay here and I'll pop my head in later.
Okay, cool.
Miss Jackson starts at 11. For well, I don't know about. Might be different for period 3, but for period 4, it starts at 11.
Okay, cool. Thanks.
Okay, cool. As always, you are free to say, sorry, Miss Jackson, and then start busting into your outcast. But, okay, so our solids, we know all of this, right? They're fast, they're vibrating, blah, blah, blah. Liquids, the term we use for liquids is they flow, right? Those particles flow around each other because they're tightly packed, but they have some movement, right? They are allowed to actually like shift and move around each other, but they don't spread out. We're not talking about particles spreading out yet. So they slip, they slide, they flow. And then again, how much they're able to flow is going to be dependent on their intermolecular forces. So if you have a lot of forces, really, really strong attractions, do you think you are going to be able to flow very much?
No.
No, because lots of attractions are locking you in place. So if you have lots of attractions, then you're not really going to be able to flow. If you have very low attractions, then you are going to flow easily. Those particles are going to be able to slip and slide past each other very easily. It's going to feel very slick, all those kinds of things.
Miss Baskin.
Yes.
Why is water so confusing? Because I thought
hydrogen bonding.
I know, but like it's supposed to be super strong, but then it's like
but hydrogen bonding. Any answer having to do with water is always hydrogen bonding.
Okay.
Why does it have a high specific heat? Hydrogen bonding. Why does it have a high density? Hydrogen bonding. Why is its boiling point so high? Hydrogen bonding. It's all hydrogen bonding. Why does it dissolve stuff? Okay. Hydrogen bonding. It's a broken record, but it's true. Okay, gases. They zoom, they're fast, they're random. The particles are going to be really, really far. Whatever. So the things that affect gases are main things that affect gases. We're talking temperature, all right, because that affects your speed, and pressure. Temperature and pressure. Those are our main things that affect gases. Pressure is like how much are you squishing them together? Because the more you squish them together, they actually have a chance to have intermolecular forces come into play. But otherwise, we don't really talk about intermolecular forces with gases because the particles are too far apart to actually have any sort of interactions with each other. And then, yeah, of course, clearly their volume will totally change based on what you put them in. Okay. Few particle forces. Yeah. No definite volume, no definite shape. Yes. The world of balloons. Okay. So this picture, this is of your water, Sean. And I would like to point out that water does something unique in the solid versus the liquid phase. Of its 3 phases or states of matter, which state of matter for water is the most closely packed?
The liquid.
The liquid. Nobody else does that. Everybody else has the closest particles as solids instead.
This is ghetto. Water is ghetto.
Water is not ghetto. This is why ice floats.
Oh, that makes sense.
The reason ice floats is why we have life on this planet.
So, liquid water is more dense.
Yes, liquid
Than
water is
solid
more
water.
dense than solid water. This is an exception to the world of solids, liquids, and gases. For literally everything else, the solid is more densely closely packed. But because of all these little dotted lines, and remember, dotted lines are attractions, all these little dotted lines making the hydrogen bonds, you get this super neat little order with the solid water that you don't get with the liquid. So this is showing you one exception to the rule, because it's important to know exceptions sometimes. Okay. Yes, yes. Which physical state or property is incorrectly matched? What'd they give us here? All right. So yeah, clearly liquids and solids do not have a rigid shape. Only solids have a rigid shape. Gases can be compressed. Can you compress a liquid?
No.
No. No. Gases and liquids flow. Solids are clearly higher density than gases. Note how they did not put liquid in here. They said higher density than gases because that's always going to be true. Okay. Which of the following statements is false? Molecules are very far apart in gases and closer together in liquids and solids. True or false?
True.
True. Gases completely fill any container they occupy.
True.
True. All right.
Don't they also spread out evenly?
Yes, that's why you can try and hide your fart in the corner, but everybody's going to know. It's true. That's why you step out into the hallway. Don't fart in the corner of my classroom. We're all going to know. Condensed states have much higher density than gases.
Yeah, true.
Yes. Condensed states referring to either liquids or solids. And then lastly, gases are strongly influenced by intermolecular forces.
That's false.
That one is false. They're too far apart, right? Like you can't actually have a force between two particles that are on opposite sides of the room. Okay. Now, gas laws. Ideal gas law. Do you have your formula sheet out? Because let's find where this formula is on your formula sheet.
Here it is. Simply because PV equals nRT.
That's what we're doing. There's a big old box of gases, liquids, and solutions formulas. And this is the first one in there. Ideal gas law, PV equals nRT. Since you get to use your own, we can write on the other variations of the ideal gas law on there as well. So that's cool. All right, so these are the equations that are on there. PV equals nRT, the ideal gas law, that's the first one. And don't forget, all the variables are listed over onto the right, including your various different forms of R. And remember, you have to match the units of R to the pressure units, because that's the one that they're going to change. So you have to use the correct value of R for the pressure units that they gave you. And it will still almost always be 0.08206. Then the next one is the partial pressure and mole fraction one. and then the Dalton's law of partial pressure. So those are right there on your formula sheet. And the most common ones that the ideal gas law is the one we use the most often because it relates moles. And then Dalton's law of partial pressure is how we can get experimental situations in there. The variation, let's write the variation up. Okay, so it was P M equals D R T. Do you remember that variation?
Something about dirt.
Yes, I remember.
Yes. The molar mass kitty puts dirt over its pee. So it's the pressure times the molar mass. That big M is the molar mass equals the density times the gas constant times the temperature. So this variation is handy to use if they're asking you about some unknown compound. You can find the molar mass of an unknown compound in that way. And I will point out that on the formula sheet, don't forget, it does have listed that density is mass, I'm using a small m there, mass over volume. So they may give you mass and volume and you have to calculate the density to plug into the formula, but that's what you need to do. And don't forget your temperatures for everything dealing with gases, your temperatures have to be in what units?
Kelvin.
Kelvin. All right, so this has to be in Kelvin. And if you forget, it's also on there, right? Add 273. And you will note it does just say 273, not 273.15. They're like, nope, just keep it simple, 273. Okay. So you can get that on your formula sheet. If you don't have your formula sheet in front of you, you can get it later. Oops. Okay.
Just asking.
Yeah.
Can there be one of these I don't know if like maybe like near the end of like all of our review, can we just have like a class or like a little period where we just like sit and actually like do all the annotations for what we're gonna need? Because I know we've done this part and we did some stuff on atomic structure, but can we just like sit through and like annotate the entire thing?
Yeah, and I can make sure everybody's got, I can send out like a clean, a file so you can print out a clean one if you want and annotate it. Yeah.
Okay, thank
Do
you.
that. Okay.
Oh my gosh, thank you, Taylor.
Okay, so ideal gases. Clearly, ideal gases do not actually exist in reality, so we're making assumptions about them. We are assuming that they don't actually have any attractions between them. That's not true, but we assume that they don't. We assume that they don't really have any volume, which is also not true. Is that it? Yep, those are our two assumptions. They don't attract,
Well,
and they don't have any volume. That's not real.
false lies.
Yeah.
Lies.
Lies and deceptions. Okay, but this is our behavior of gases. So looking here at each of these things, we've got pressure and volume. And pressure and volume, does this represent a direct or an inverse relationship?
Inverse?
Inverse.
Yes, because yeah.
All right, that is the inverse. Pressure and temperature.
Direct.
That is direct. Volume and temperature.
Direct.
Direct. And then do note here that this thing That is the inverse of pressure. So it's showing that for pressure and volume, to get something that looks direct, you have to use an inverse function. So these two are showing the same thing. All right.
Oh, so that one's
inverse.
Yeah, I mean, it's still showing that there's an inverse relationship between pressure and volume, because to get a line that looks direct, you have to use inverse of pressure.
I see.
Yeah. And then, so you don't have to know the names of these guys, but pressure and volume was Boyle's. And then...
oh my gosh, I remember we were going through all the different men and their different ideas.
Volume and temperature was Charles. Charles, that's totally an R. L, that's totally...
It's okay.
That's a question mark.
Charles!
That's about how my dad writes his name. He's a Charles. Pressure and temperature, that's Gay Lussac. I am not writing that out. And then this last one, we've got
just
volume.
Put JLS or GLS.
How about this? It's just gay, so gay. We all remember gay. Okay. Volume and number of moles. Whose law is that? Because this is also direct.
I don't know.
The number of moles should make it easy.
Avogadro.
Avogadros.
Avocado.
Avocado.
Ooh.
Avocado.
All right. We got avocado up in there.
Yeah.
Okay, so you don't have to know those names, but it does kind of remember. So basically, you remember everything is a direct relationship except for pressure and volume. Like literally everything else has direct relationships except for pressure and volume. And this should all be common sense for the most part, remembering all of this. If you put more shit in a balloon, it will get bigger. If you heat up a balloon, it will expand. If you increase the temperature inside a closed container, the pressure will build up until it explodes. But if you squeeze on a balloon, it will get smaller, right? So it's all common sense. Okay. The Dalton's law of partial pressure. This is when you involved multiple different gases that you were all shoving together. So this is one of, I think this might be the only formula that has addition. It's simply it's easy. The total pressure is just the sum of all the little baby pressures, right? You have to have multiple things in there.
But don't they all have to be the same unit?
Yes.
Of pressure?
Yes.
I remember, I don't know why, I feel like that was the most tedious part, like having to convert them all into one.
Make it all
and does it
atmospheres.
matter which one?
Yeah.
Wait, what?
Oh, yeah, okay. All ATM. Oh,
yeah, they're either going to be all, you're only ever going to see atmospheres or millimeters of mercury.
Okay.
And they even have that conversion factor on there for you.
Where?
On the right-hand side,
Right side.
below the gas constant, it says 1 ATM equals 760 mmHg.
Okay.
Yep. Yay. Okay, so every gas's pressure is independent of everything else because they don't really care that there's other particles there. It just depends on the amount of particles of a specific gas. So it's a little different. I will say that Dalton's law of partial pressure, this came into play in the collecting gas over water. That's how we primarily spent time doing it. It was the collecting gas over water. And we did a lab on that. You remember where you guys had the buckets and you stuck your hands in?
Yes.
No.
Yes.
I didn't stick my hand in anything.
We had to like put a tube in a thing and then pick out. Wait, no. Yeah.
So we slowly,
in
you had these tiny, you had the thin glass tubes, and you put a little bit of acid at the tip, and you filled it up with water, and then I gave you a little piece of magnesium,
Oh yeah, I do remember that one.
Right, and you stuck it in and you turned it upside down, and then as the acid slowly fell down, it started reacting, and then the tube filled up with water. So when you are collecting gas over water, not of water, that's over, you have to subtract out the pressure of the water in that gas, right? Because it's not what we call a dry gas, it's a wet gas. It's wet because of the water. And so to know what your actual pressure of gas is, you subtract out the vapor pressure. So that's what we normally end up having to use Dalton's law, is you have to remember to subtract. So I'm just gonna say subtract vapor pressure. And it'll be real obvious if they give you this, a problem where you have to do this, because they will give you vapor pressures values for water. And you're like, why do I have this thing? The only reason to have it is if you have to subtract it. It's literally the only reason they would give it to you. They also are probably even going to have a picture, and therefore you should recognize that we're doing that. So I think another thing, in addition to Sean's suggestion, is we should go back through the labs or the lab techniques we've done, because the chances of one or both of these questions being lab-based questions is really high, because they've been moving in that direction anyway. And a lab-based question is not something that would be Googleable. If they like give you lab data and ask you to do stuff with it, like you can't Google that. You just have to like know how to deal with it. So I do think that that's a good possibility. So we'll do that as well. Okay. Oops. Let that go away. Okay. So you got a calculator? Because we got an ideal gas law equation.
I have it.
Okay, so this first one, mixture of gases. All right, so we got a mixture there. Mixture of gases contains 1.5 moles of oxygen, 3 moles of nitrogen, and a half mole of water vapor. If the total pressure is 700 millimeters of Hg, what's the partial pressure of just the nitrogen? So do you remember, what do I do with these mole amounts?
Turn them into gases.
I don't have to.
I lied.
Of the 3
Which one?
formulas that they went over, is this the first one, the second one, or the third one?
Well, this
Partial pressure.
Oh wait, no. Is it the last one with the P total and then the PA plus PB?
If I had all of these as pressures instead of moles, it would be.
That is true, if there are P's. Okay.
Oh, so it's the second one?
It's the second one.
Okay.
XA.
So I want the
Moles.
pressure of nitrogen.
Okay.
So that's going to be, the formula says it is the pressure total, right, times that mole fraction thing. And what is the mole fraction?
The moles of the nitrogen
So the moles of nitrogen
over the total moles.
over total moles.
Oh, I see.
Okay.
Oh shoot.
So it's 5. Do we include the water vapor?
Yes. So my moles of nitrogen is 3. My total moles is
5.
5. So it's 3/5 times the pressure of 700. So what's that?
Wait.
So do we need to, at this point, can we leave it as millimeters of mercury?
Absolutely.
Okay. 420.
420.
420. Blazing. What's kind of my day? I don't know what's my day.
Wait, I was confused. Okay, so.
Yes.
So we put the 3 in the mole of nitrogen because there are 3 moles of nitrogen.
So
And the
that
total
number, so the pressure total is 700.
Okay.
The moles of nitrogen is 3.0.
Ah, okay.
And the total is adding up the 1.5, the 3, and the 0.5.
Right.
So
Which is
that's
5.
5.
Mm-hmm.
No.
So
Okay.
700 times 3 divided by 5.
Did it.
Okay. Okay. Now, if 2 moles of gas in a sealed flask is heated from 25 to 50, what can be said about the kinetic energy, the pressure, and the number of moles? So first off, are they asking you for a calculation here?
No.
No.
No. All right. So don't start doing a calculation if they don't actually ask you for one. They're saying what's going to happen. So what is the condition I am changing?
The temperature.
I am changing the temperature, and I'm making what happen to my temperature?
You're increasing it.
I am increasing it. Okay, so if I'm increasing my temperature, what can I say is going to happen to my kinetic energy?
It will increase.
It should increase. What about my pressure?
It increases.
It should increase.
Increase. And the number of moles?
Should stay the same.
Stay the same.
No one else can answer.
And the reason I can say with certainty that the number of moles stays the same is it says it is sealed. Right? Meaning that nothing is going to go in or out.
Okay.
Okay. Okay, so a sample of 18 grams of aluminum metal is added to excess hydrochloric acid. The volume of hydrogen gas produced at 0 degrees Celsius and 1 atmosphere of pressure is approximately what? So this is asking for a calculation. And to be able to do it, I actually have to have a chemical equation first. So we're going to use PervNerd. So what you need to see is, do you have the P, the V, the N, the R, the T? So mark up, what did they give me?
Okay, so they gave us the pressure.
T.
I have a P.
T.
Volume.
I have a T, right?
I have a
I
T.
mean, it's 0, but it's still T.
Right, so what is it in Kelvin?
273 degrees.
273. So I've got a P and I've got a T.
Mm-hmm.
R
We
is a
can
constant.
Can't you convert the grams to moles?
So that means I need to use this value to get moles. Yes. Okay. And which letter am I looking for?
V.
Volume.
I'm looking for the V. Okay. But that's 18 grams of aluminum. Is aluminum a gas?
No.
No. So what I need is a balanced chemical equation. I'm adding aluminum.
I see.
I'm adding
to like acid.
To acid. Okay, so aluminum, and they're not going to do this to you. They're going to give you a balanced equation, like we already know that. Hydrochloric acid, do you remember that formula?
HCl.
HCl.
Miss Baskin, this A is nice. I like it. It came out great.
I know, it was very clean.
Thank you.
Very pristine.
Okay. So what do I know my products to be?
Water? Nah, that's a lie.
No.
Oh, wait.
They tell me one of them.
They do.
What?
Hydrochloric acid.
I don't know what's happening.
Oh, hydrogen.
Hydrogen gas.
Okay. How am I writing hydrogen?
Lisa, I can't with her.
H2. And what's my formula for the aluminum and chlorine?
Al2, AlCl2 or Al2Cl.
Al2Cl3.
AlCl2. 3.
Aluminum's a charge of 3, chlorine's a 1. Okay, so balancing.
I wrote that wrong. Go ahead. Yes, please. Yeah. 2, 2, 6, 3.
You
We
know you're
did
gonna have
it.
to use
Yay.
3s and 2s because of these two guys.
Answering machine, Sean.
See.
My answering machine is on.
I said when you said 2.
2.
Oh.
Sound like
I was like, what?
You were like, sorry, what? Okay,
An answering machine.
so we did all of that because what do we have to do with this guy?
Find a mole.
Converted to moles.
Converted to moles. So 18 grams.
Oh, wait.
All right, 18 grams of aluminum. And I'm going to cheat here and say that aluminum is 27 instead of the 26.998. So 27 and 1 mole, except I don't want aluminum. I want hydrogen gas. So what's my next step?
2 moles of aluminum to 3 moles of hydrogen gas.
All right, 2 aluminums to 3 of the hydrogens. Now, if you will notice, 18 and 27 are both multiples of 9.
Mm-hmm.
So 18 and 27 can both be divided by 9. So there's 2 on the top, 3 on the bottom. So this actually equals 1 mole. You can do it in a calculator, double check me, but that equals 1 mole.
Damn.
How do we end that?
Go.
Why
That
do we
was
convert it
that
to
was
the
nice.
hydrogen?
That's why she cheated.
So the reason we had to convert it to hydrogen is the gas here.
Okay.
So Pervner
looking
will
for
only
her.
work with a gas. Aluminum is a metal, hydrochloric acid is a solution, and the aluminum chloride is going to be in a solution.
Uh-huh.
So now I have 1 mole, 1 atmosphere, 273 Kelvin. What's my volume then?
You said we have 1 mole, 273.
Uh-huh.
What is R in this case?
We'll match the pressure. Match the pressure unit.
Wait, could we use the, I don't know. Can we use the 18 for the volume?
No, you're
Convert?
finding volume.
Oh.
So is
I'm
the
tripping.
because 760 millimeters of mercury and there's 760 torr, do you use the same number for torr and mmHg?
Yeah,
For
but I
R?
don't care about that. I'm just going to use 0.08206 because that's atmospheres. Use the R value that matches your pressures.
I don't know why. I think I was thinking back to the last time we did. But yeah, okay.
So I have
okay.
1, which is the P, and then which is the P times V equals 1, which is the mole, times 0.08206 times 273.
Yeah.
Okay. Which is just 1.
Is that what you're getting?
Hold on.
I haven't done it yet.
273. Yes.
Yes, Kayla.
And this can, I was about to ask you what unit's going to be in, but it's volume, so it's
yeah.
Yes, I got that too.
Okay, now you're going to be mad because there's a way to do this without any of the calculation, and that is recognizing that I have 1 mole at STP.
Sean, you okay?
Yeah, I was wondering. Sean's in a dance party in his own room. So I have 1 mole of gas at standard temperature and pressure because Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere, and I have 1 mole. And that, by definition, is
wow, Miss Zach. You always.
I want to cry. Like, you know what?
You always doing too much. I think personally.
It's like you
simply because I feel like you took us through hoops and ladders.
No, because I made you remember what the hell it is you need to do.
I know, but it was like, wow, but you have to do it under the guise. Like, it was a trick. I felt tricked.
Yes.
I felt betrayed.
Whatever, you'll get over it.
Hoodwinked and bamboozled.
So the next one, nitrogen gas was collected over water. That's the lab we did at 25 degrees. If the vapor pressure of water at 25 is 23 millimeters mercury, and the total pressure is measured at 781, what is the partial pressure of nitrogen? Again, the only reason the only reason they are ever going to give you this is so that you can subtract it off the total. That's it.
What was that, 58? 758?
Woohoo! Yes, mental math.
Yes, I've been getting better over this past year.
And now you don't even have to do it because everybody can use a calculator.
I know, which is tragic. I was building that skill up.
I mean, it'll be good for you.
Yeah, it'll be good later in the life.
Later in the life. Okay. Kinetic molecular theory. This is all just like, hey, the particles, they move. Right? They move faster with more temperature. Okay. So they constantly move, right? We know that. The volume of those things doesn't particularly matter. The attractions don't particularly matter. The collisions and all that sort of stuff are elastic. And then basically the average kinetic energy is the same thing, or is a measurement of the temperature. It is the average kinetic energy being the temperature. So we know all of those things. Yeah, so the average is the Kelvin temperature. They have never in all of my years ever asked an equation or a question that has you use the equation that's on your formula sheet for this. But if things are at the same temperature, they will have the same average energy. Okay. But what we did say was this part. More massive particles are going slower. Does that ring a bell?
Yes.
Yeah.
Yes.
Yeah.
Say that one more time.
In order for everything to have the same energy at the same temperature, the heavy guys have to be moving slower. The smaller guys have to be moving faster. That's how they end up with the same amount of energy.
Okay, yeah, makes sense.
Okay. So that's all that equation is showing, but they've never, ever, ever asked anybody to do a calculation with that equation. So I ain't worried about it. You remember that graph? We did a whole lot of these graphs when you came back.
The devil.
Oh my God. I'm trying
the devil.
Okay. So this guy, that's the xenon. So whenever you get graphs that have multiple things, you should always look at the extremes. So let's look at this highest one and let's look at this flattest one. So xenon versus helium.
Mm-hmm.
What's the main difference between those two things? Size. Okay, so this guy is the small, other one's the big. So, and this is basically showing you what about the speeds of those two things?
This is showing us that helium, on average, has a faster speed than xenon.
Yup. That's literally all that graph is showing. All right. Okay, so I got some neon and some argon in a container. What can be said about the average molecular speed and the average kinetic energy of these gases? Again, there's no calculations here. One of those is easier to tackle than the other.
The kinetic energy is the same.
Yes.
And the average molecular and neon is on fast. Again, is faster on average.
Yes. The neon is going to be faster.
Ms. Baskin?
Yes.
Is it because at the same temperature that the average kinetic energy is the same?
Yes.
Yay.
All right. So this fact here is what tells you that these are the same. And we know neon is faster because it's got a smaller molar mass. All right. Okay, true or false? In a sample of gas at a constant temperature, the speed of all the gas particles will be the same.
False.
Correct. That is not true. They average out to be a certain value, but the whole point of that distribution graph was to show you that their speeds are a distribution. That is the point, that they're spread out. They are an actual distribution. Okay. So if I have a 1 mole sample of nitrogen and a 1 mole sample of argon in 2 different containers, and they each have a small little opening, which one will be slower to effuse, which means to come out?
The bigger one,
Okay, so
right? Isn't it the bigger one?
So, well, you got to know which one is the bigger one. So what is the molar mass of nitrogen gas?
14.01.
Nope.
Oh, 28.02.
28.
Oh, because there are two. Oh,
It's
that's
diatomic.
Yeah.
Yep. And
What are
what
you
is
talking about?
what is argon?
Is it AR2 or is it AR?
It's just
Oh,
AR.
wait, no, is it just one?
Yeah, it's
Oh,
just
then
one.
39.9.
Okay. So it's 39 point something. So which one is bigger?
Argon.
Okay, so who is going to be slower to effuse?
Argon.
Argon.
Ooh.
All right. So again, remember, like this is, it's not hard. You just gotta remember to go through the things. Okay, so that's where we're gonna go for today. We did not finish. I knew we weren't going to finish because there's so much crap in here. So we're gonna finish this slide deck on Monday because again, we don't have class on Friday because it's Records Day. So we're going to finish this slide deck on Monday, and the collaborative notes are not due until Wednesday of next week, and the Unit 3 personal progress checks are not due until Friday of next week.
So, Ms. Baskin, have you heard any word about what grading is like for? Because I know you. Okay.
Nope.
I know you were saying like because there was a baseline they could go off of for a period not unit for term 3.
Yeah.
They couldn't like deduct past a certain amount, but because there are no grades for term 4, so do you expect to be hearing anything soon, or?
I expect that they're gonna tell us maybe a little bit of something on Friday, but like even admin yesterday said like, dude, literally we've gotten no information about term 4. You know, I know teachers over at Coolidge, so it's always nice to double check what they hear versus what we hear. And they're in the same boat. They're like, nope, our admin told us that we've literally heard no information. So
Yeah.
nobody knows anything.
Coronavirus.
We're gonna fail. We're
So-
doomed. I'm transferring.